This is Mastering Mathematics with your teacher, Karen Weston.
Welcome to Mastering Mathematics, production from the Ministry of Education in conjunction with ABS TV. Last time we were here, we introduced the topic sets, and we did defining a set, elements, number of elements in a set, finite and infinite set, the null or empty set, the universal set, subsets, the number of subsets. And so today we're continuing with our definition of our sets. And we're getting right down now to start talking about equal sets. And this is the same as what we use the word equal to signify in the real world, where we have equal sets. Okay? And we say if we're given the set A, which is equal to 10, 11, 12, and 13, if we give you another set B, and we want that set to be equal to A, then the elements have got to be exactly the same. The elements have got to be exactly the same, so that we can have 11, you can have 12, you can have 13, you can have 10, okay? The order in which they're written does not matter, but they must be identical. So you're getting 10, 10, 11, 11, 12, 12, 13, and 13. And this is how we say that the set A will be equal to set B. All right? So equal sets, they are identical, they have the same elements and the same number. In contrast to equal sets, we can have equivalent set. Equivalent sets, okay? And this time, what comes into play here is that the number of elements in the set must be equal, not that the elements have got to be identical, okay? So for example, I can give you a set C, which is equal to 1, 2, 3, 4, and the set D, which is equal to A. When we write in the elements, we don't use capital letters in our brackets. We use the small letters, so it's A, and it's B, it's C, and it is D. All right? We would say that those two sets are equivalent, okay? Because they have the same number of elements. So when we count, so it's really counting and seeing that we have 1, 2, 3, 4, because NC is equal to 4. And when we count again, ND is also equal to 4. And therefore, NC would be equivalent, okay? Equivalent. Don't want to give you that wrong symbol, so I'm not writing it. Equivalent for ND. I think we use something like a little wave to talk about equivalent, but we leave that for now. But just to give you the word so that nothing is given to you incorrectly, because it's very hard to unlearn something when it's taught and it's the wrong notation. Okay? So again, we make the point that equal sets, they have got to be identical. The things must be the same. Now, equivalent set, you can go to your granny's house and you can say, uh-oh, you come late, so you didn't get all the mangoes, but I still have. So she got 4 mangoes, but I will give you 4 pomegranates. And it's still equivalent sets, all right? So that is what we're talking about when we talk about our equivalent and our equal set. The next thing that we want to talk about now is getting you to see things visually, because you've been hearing a lot of things. Nothing has been coming out. Do we ever draw in this thing? Yes. For some of the things that we're going to get when they give you the words and the problems, what we do, we represent them in diagrams. And in SETS, the name of that diagram is a Venn diagram. Venn, because it was just named after the person who actually invented the diagram and the notation for that diagram. And what is it made up of? It is made up of the rectangle.
Whenever possible, draw a diagram. Even though you may be able to visualize the situation mentally, a hand-drawn diagram will allow you to label the picture, to add auxiliary lines, and to view the situation from different perspectives.
And then we get our circles, okay? So this is what we'd be calling our Venn diagram, all right? So, okay, so the Venn diagram will tell us then that we have our universal set, and then we can have a subset, which can be called S, okay? Our subset. A Venn diagram is made up of our rectangle and the circle. Once we start getting into universal set and subset, because that is what the circle represents inside of the Venn diagram, the whole rectangle would tell us that we're into something where we have our universal set. So, for example, up here, I can say that the universal set here could have been represented by 3, 6, 9, 12, 15, and 18. All right? And then I could have said that my subset would have been where we have the numbers 9, 12, and 18, okay? Now remember that the whole diagram represents the universal set. So once we have taken out a subset, the other numbers have to occupy a space in the rectangle. The numbers which are not in the subset, so for example, 3, 6, 15, okay? These numbers, they're not in the subset that we have just formed. Those numbers which are part of the universal set, but they are not in the subset, it's called the complement of the complement S. All right? So that would be called complement of set S. So when we use the word complement, it refers then to members of a universal set which are not part of a subset for this universal set. So hence, since we have S, first we have the universal set, and it is equal to the set 3, 6, 9, 12, 15, 18, and then we have a subset from that, which is S, which is equal to 9, 12, 18. The complement S, so S complement would be equal to, and we have our sets 3, 6, and 15. Okay, 3, 6, and 15. So that if we had to join our S and S complement, that would have been equal to our universal set. Okay, that would have been equal to our universal set. Universal set. So we would expect then the set 9, 12, 18 and the set 3, 6, 15 to give us back our universal set, which would be our 3, our 6, our 9, our 12, our 15, and our 18. Just writing the numbers in order from smallest to the largest one. Okay, so everything will be thrown back here. What do we notice that I am doing? I am using the word and. But there's no place for this word and when we are using set notation. So we have something that takes care of that. Certain times when we're adding, we're subtracting, and we're multiplying, we use our equal sign. In set notation, there are two items that we use to take care of those things. We can either be talking about union or we can be talking about intersection. All right? So we don't use the word and. So in here, instead of saying S and S complement, we'd be using S in union. And union has this upside down U2 that really looks like our universal set. So sometimes that is why we see a little tail that's added onto the universal set to distinguish it from the notation for our union. Okay, so the union has the same upside U, and so it is written like that, an S complement, and that would be equal to the universal set. So we give it a little little tail to make certain that it does not look like this. Okay, so we never use the word and, we use the word union, the symbol union. Okay, union and not and. So that is what we do in terms of mathematics. And that is why I'm saying that in the mathematics classroom, we've got to make certain that we know that the children, that they're comfortable. We've got to take time as teachers to give them the vocabulary. Mathematics has its own language, particularly words which are only spoken in and within the context in which it is being done. And we cannot expect students just to come and grabble and hold on to the term. We have to keep repeating them. They're not their everyday language. It becomes a part of them when they see it as part of the discipline. So we have to keep reminding them, making certain that you're telling them all the time, go back to your definitions, make certain you know that, because you have to start speaking like a mathematician. Can't be saying, I know how to do it, but I can't explain. We have the vocabularies, so we have the words, and you're going to use them to talk the mathematics language than what you want to explain. All right? So teachers, again, we have to take time to make certain that we give them the definition. Okay? So our first point and first order in a mathematics classroom is to make certain that the vocabularies associated with the language is understood. So here we go again. So this is where we are so far, talking about our union of the set. So the union then represents putting, when we have several, if we have several subsets from a particular universal set, joining them together, where in another aspect for mathematics we'll be talking about